So then, I hope you remember that this is the last 2 sessions we are going to have for this semester. Okay, do you feel like exciting that the semester is almost end?
No.
No? I feel exciting. Okay, yesterday when I even prepared the next week's one and the week afterward, and in the December 15, and then I think for our final project in the December, because I was thinking about how the demo supposedly looks like, and it could be interesting. So I think in the December 15, I don't know, it's 15 or 13. Am I say the name time correctly? 15? Okay. So December 15, actually we will still meet right here. Sorry, but we can actually get up a little bit late. How about not 9 o'clock? We can start a little bit late, and then you can have 1 more hour sleeping. Would that be better? Okay, so then I will make the TA to send an announcement by December 15. We will still meet here, but we will not meeting at 9 o'clock. We meet at 10 o'clock, since it's a final project day. And then we will try to go work with you, and we will handpick some interesting video, but not as many as in the progress report. Why? We probably will, every competition, we probably will only pick the 3 ones that are very different from one to another one. And you actually have ability to go through, see all the project, because in the final project, we are going to group together on a place, a virtual place called Gather Town. Okay, so in the demo project day, right here, we just walk through certain Gather Town, and like every competition, we only walk through for like few, just like 2 or 3 projects, and then I will also give you some final remark. I always want to do one thing. I'm teaching for more than 20 years. I know in the NTU, there are some professors, they're always very famous. In the end of the session, they are going to somehow summarize everything of the classroom, and not only about the classroom, it's about the important classroom concept with a life attitude. I feel like that is interesting. So let me try to see if I can mimic and try to salute that idea. Okay, so that is a part about our final project. So in the final project day, we still meet, but that will be in 10 o'clock. So everyone can have 1 more hour sleeping. And for today, that is the last part for the classroom analysis. Actually, it's quite interesting. You will find out that most of the time, traditional data mining course, how we usually try to align for all this concept, the topic that we try to working on. We probably were starting from one session, like a data, introduction data that we did. And afterward, usually people will go to association rule. And then after that, they go to clustering. And then after that, they go to classification. And then after that, they go to some special topic. You will find out that our order are quite different from the conventional data mining. And why? Because we also team up with some competition. And then before, some of the final project we have is we did not attend the competition, so we can have our own path. But I feel like having a competition, one thing is good, is because you guys actually can see how you perform through the private leaderboard or public leaderboard. You know how you are going to perform. And then by sharing each one of the groups, so we handpick some good team right there, you will realize one very important concept, that is garbage in, garbage out. Right? Because you will find out certain group, they're doing so well, is because the way they try to process the data are different from you guys. If you just try to do the traditional data engineering, do something very common, and then you'll find out you're always stuck in certain place. But then if you do something extra, utilize different strategy to working with that, that usually can improve your final project's leaderboard standing. And then why the association rule and the clustering in the conventional data mining courses are usually being placed in the beginning? Because those techniques actually has been invented earlier. Okay, so if we actually go through the timeline, we usually starting from earlier one and then go to the most needed one. But if we went through that, we are afraid you guys will suffer a lot in the final project. That is why we do certain arrangement. Okay, so clustering, the last time we were already talking about the part 1, and I'm glad that in the 1 minute reflection, some student asking that, for example, there's one student saying, Professor, can you clarify the clustering technique more? I would appreciate about it. Yes, I would like to clarify, but I cannot repeat the 3-hour session, right? So if you have any concern, you need to let me know which part that you do not understand. So please remember one thing, that you shouldn't just ask people to repeat everything, because sometimes maybe you just need to clarify on like a 5 minutes part or like 2 minutes part, but you need to learn to explain which part stopped you, or you got stuck at which point. Okay, and so today you actually will find out that this is our online. Again, we will go for some QA, and then we will revisit the hierarchy clustering. I went through the slide, the Google slide yesterday to check what you wrote. And then I'm sorry because I'm not so sure why sometimes I think I'm changing the link, but that did not reflect. Maybe I forgot to save or do some other part. And then I realized like many groups already work with it. Of course, some group probably working on the wrong file, we did not know. And then you will also find out that we list certain thing called optional. Okay, so in the optional one is I usually are not so sure how long I will able to cover. So if you find out, if I indicate what is called optional, then usually the slides are most complete. They are all, I cannot guarantee it's 100% complete, but it's at least like 99% complete. Unless they do having some picture that I don't own the copyright. Okay, so then I usually did not reflect to the parts that, so please ignore, I think I make the animation incorrect. Yesterday I saw a question from November 3rd. Usually I don't review the question 2 weeks before, but that is a great question. I would like to utilize this one today, okay? The student asking that they do not understand, because in the LLM part we mentioned if you put a lot of junk into LLM, and then afterward, no matter how many clean data you input to refine that, they still remain damaged in some way. They still cannot perform as good as they did not see the junk data before. So it's more like it cannot recover. So then that is why we're thinking about that, and thinking about one way to talk about story. Just my guess, this is my guess. You're putting a drop of the poison into a soup. Because LLM, you have so many data, and after the data go into the LLM, and the effect of each part of them is like go to the tiny, each part of them go to all the weights. Okay, so it looks like you putting a drop of poison into the pot of soup. And then afterward, the soup become poison, right? Then you put so many good ingredients afterward, the soup's still poison. That is the reason why the LLM cannot be reversed. You can say that because putting so much water, so much ingredient, and you dilute the poisonous. But they still poison. Okay, I think that is it's an interesting one if you actually see that. But, so, I feel like it's interesting because no matter what you did, you took these courses or withdraw this course. Okay, everything you did, I believe, that is my belief, that leave some imprint, leave some trace in your life, even though that is unseen or like almost cannot be recognized. But that no matter what, everything come afterward, what you did leave an imprint. So the interesting part for the LLM, what we try to talking about is we take that as a lesson. So in every imprint, I believe it can become a lesson. You can make that as a guide. You make something wrong, don't try to say, oh, I regret about that, and then try to get away from it and try to avoid it. No, make them to become your compass. Then one day, you're grateful for every mark, no matter they are positive or negative. I think that's interesting, so that's why I want to say about it. And also, one more thing is LLM, the good part of the LLM is we remember every parameter value from some hard disk. So even though we say it cannot be a revert, but you can directly reset the parameter setting. Our life did not. We don't have a parameter, a set of parameter, and say, oh, everything I do that, I regret, and then can you help me to erase and resetting my thing? No way. So they're just thinking about make those everything you did as a compass. Okay. So this is a question from the 2024. I think it's a good question. They say because last time this part, the elbow technique that we did not talking about, so maybe later. I think we will mention about that a little bit later. And then they say, but if the clustering results are not satisfied, what might be the next step? Okay, first, check your result first. And most of the time, you will find out the things are not good. Usually, it's because you did not pre-processing well, or you do not choosing the correct technique that you try to working on. There's two major reasons because of that. And in this question, there's one thing we're talking about the elbow technique, and then I did not mention last time. So what it meant? We say K-mean, K is important, right? And but then the problem is I don't know how many things I need to set up for the K. So what can I do with it? Usually, in reality, we try different K. So, right here, give you some example. We might try, this is K, okay? We try K equal to 5. We can try K equal to 20. We can try K equal to 100. And then we can continue trying many different things and see how the result looks like. And then how we can measure them. Assume this one is sum of square arrow, so that is arrow. You know usually what it looks like. If you increase the K, sum of square arrow will, then try on that. They will go up or they will go down. If I increase the K, sum of the square arrow will go up or down. You think it's up? Raise your hand. You think it's down? Raise your hand. Great. So why down? Because if the K is increased, the element inside every cluster actually becomes smaller, right? So of course they will get closer to the mean. So you will know the trend is look like this. Okay? I mean, if in the end, so assume you have 100 points. If you go to the K, you will know that sum of square arrow will be 0, right? Because every point is itself mean, so that will become 0. So far so good? Okay, so but you don't want to choosing the smallest sum of square error. You feel like it is weird, right? I do the cluster, I want them to be grouped, but you actually are not going to. So let me try to utilize different color. So you know the trend. The trend is doing like that. So in some way, the sum of square error for a certain k, they will go to 0. But in reality, they do not perform like this one. They might. This one is not reality, okay? So in reality, let me utilize, go back to the purple color. It might look like this. And in some point, this one will go drop to k, okay? In reality, it might look like this. Or in some cases, I don't know, because most of the time it look like this. But maybe in some very extreme cases, it might look like this. But this one is rare. I have to tell you, I did not see much of this one. I only see, I most of the time see the purple one. And when we say L-bone technique, is because right here you can see there's some turning point, like right here. If you do the calculus, you will know you can find a turning point right here. And that we actually consider is an L-bone, right? And this one, if you can find this one, this may be a good K that you can working on. So that is a technique how we usually try to find a K. We try and error, and we find the best K right here. So like in these cases, if I have this purple line, and then I try to find the K, maybe right now is K equal to 18. So maybe make the K equal to 18, or you want to be safe, make K equal to 20, it will be better than 5. So that is some try and error study that we usually did. Okay, so then go to the next one. And this question from this year say that does a K-mean produce cluster with similar number of the element because it cannot handle cluster of different size? Because last time we showed you the K-mean cannot handle the cluster of different size. It would tend to break the large cluster into the smaller one. That is what we said last time. The answer for this one is no. K-mean do not really make the cluster of the same size. It will, most of the time, they will actually just try to see, because K-mean usually is talking about the distance, okay? And then they will actually emphasize on distance. So even though there are so many different elements inside, but then in the end, if you find out that this one is only 3, this one has many, that is very, very possible, because they emphasize on the distance. And why we say sometimes a big cluster probably will break, because maybe this is a big cluster, and then because they are just too big, the distance are too big, so the K-mean will tend to break them to the smaller one. So that is why last time we said K-mean are usually cannot handle the cluster of the different size. Okay, and then sometimes here, this is also a good question. Say that I don't really understand the difference between K-mean and K-mean-ODs because maybe we go through them very quite quick. Last time I went through certain part very quick enough. It's because I would like you guys to go to the hierarchy clustering and go back to think before I talk today. Okay, so let's try to see K-mean. The reason they call mean is because the centroid actually is utilized. The representative is the average of that cluster. So mean, the K-mean is K average, and mean is a cluster representative. And most of the time, the K-means, their centroid are not necessary to be a real point. It could be a virtual point. It did not exist. But when we try talking about K-mean-OD, actually, they do not utilize a virtual point. They utilize a really data point. And this data point, last time we go through them very quickly, the concept is it actually the point have the smallest total distance to other in the whole distance in the whole cluster. So that is why they keep on trying which one actually have the smallest distance sum of the distance through others in the cluster. If they are smallest, they will switch to that. So that is K-mean-Yodi. Okay, so that's the difference between these two. Okay, great. So then we will go back to review the hierarchical clustering. Okay. So this part we already know that hierarchical clustering actually have two parts. They have bottom-up approaches and bottom-up approaches or top-down approaches. And what we try to talking about in this class, we try to emphasize the bottom-up approach, how to make a hierarchy. So in other words, is you were having so many clusters, so many clusters, and then we do bottom-up. So we say, these two are quite similar, so that try to put them together. And then after that, these two are similar, and then these are similar. And then after that, so then in the end, we probably will do some hierarchy. So that is what we try to do with this clustering. Okay, so let's try to see some example, because last time I kind of sent you guys to go to do the example. The first things, when we try to talk about hierarchical clustering, we actually introduce a concept called proximity matrix. Okay, and that is a term we did not mention before, but it's a term it's quite easy for you to thinking about. Proximity matrix is a matrix try to record that how similar the 2 point or how much distant this 2 point is. We use as a different term called proximity because they could be distance measure. You know, if there's distance measure, the higher the worse, right? The least, the better. Do you understand what I'm talking about? If that's distance, I want the point they have the smallest distance. So the lower, the better. Okay, but if the proximity matrix actually keep the similarity value, then you will hope then they could be the higher the better. And the proximity matrix is one that we try to emphasize on that. So that you can utilize distance, you can utilize similarity, depends on you. But then once you put them and try to having a matrix to indicate the relationship between the point, we call them proximity matrix. Okay, so that is why we have the new term. So then the button approach for this hierarchical clustering this way is we're starting from every individual. So just assume this is their individual. Just so the proximity again, that is about how near they are. Okay, so after a certain place, assume, okay, because I don't want to go through so many steps. So I just assume we already go through this different part and have this 5 different clusters. So I'm going to starting to working from this 5 cluster. Okay, so then right now you actually see the cluster numbers C1, C2, C3, C4, C5. You also see that because of distance or like the similarity values way, some of the cluster have more point. Some cluster only having like 1 point. That is very common if that is K-mean related concept. And then this part is we ask you to go back to think. How can we define the inter-cluster similarity? So after I'm merging them, so for example, assume I want to merge these 2. Assume I want to merge these 2. So then you will find out C3, C4 will actually be merged. C3, C4 be merged. And afterward, like right now, let's try to see this one, C2. C2, actually the distance from the C2 to C3 actually is 19. From C2 to C4 is 16. Okay, so when we say how we define the inter-cluster similarity is we have 19 and we have 16. Okay, which one will be the one to be used for the updated proximity matrix? I should utilize minimum value or I need to utilize maximum value? or I actually try to do the group average. I can have so many different ways to working with that. But in the class, because of time, I only want to study the mean and the max because they are totally opposite. Okay, so then I try to give you some example. So assume this is a mean. The same cases today, I actually will merging between C3 and C4. Do you know why? Because C3 to C4 is 8. C4 to C3 is 8. From my perspective, when we are doing the clustering, we try to merge. We merge the cluster, have the smallest distance. Right now, assume these proximity matrices are distance value. So I want to merge the proximity matrix based on the smallest distance. So first good, smallest distance. And then afterward, I will say, okay, I want to merge this one. Okay, but how should I update my matrix? So right now you actually can see, I name the merge cluster as C3 plumb. And then you actually can see I already having some highlight value. Let me try to tell you how I try to working with that. C1, you have C3, C4, and then I have 16 and 18 for me to choose. Because this minima strategy to define the inter-cluster similarity, so then I choosing 16. Okay? Because 16, 18, I'm choosing 16. How about C2 to C3 and C4? Still, 16 is the smallest one. So I also choosing the 16. So you can actually try to working with that and then find out that in the end, what we did is we're choosing the smallest one. So that is update proximity matrix. So first good. And the next step, so then we're starting from right here. We're starting with the update, the previous update proximity matrix. And right now, we actually try to find out which cluster we need to merge. And then it turned out we need to merge C2 and C5. Right? Because C2 and C5 are the smallest. So first good. So then our update proximity matrix will be this one. I think I don't need to talk about why they become this one. If you need, let me try to say it again, because for example, right now we have C2 plumb, and then C1, C2 plumb, and C, so this is C. Sorry. This is C2 plumb. This one, and this one. Okay? And then so C1 to C2 plumb actually is C2 and C5, right? So 11 and 17, we're choosing the minimum one, that is why it's 11. If you go to each one of them, you'll find out we usually try to choosing the smallest one because this is the strategy we try to adopt, minimum one. And afterward, that actually we're having this one. And because they're all the same, so I randomly pick, assume I randomly pick C2 plumb and C3 plumb. Assume I pick this one. So in the end, the update proximity will become something like that. So first good? Okay, so you see how it looks. Let us try to go through the maxima strategy. The same thing, again, what we need to merge, C3 and C4. So you can see in this stage, they are the same. And then how about proximity matrix? We're choosing different thing. So C3 and C4, 16 and 18, we're choosing the largest one, 18. Okay, so every time, so different from the minimum one, every time we're choosing the maximum. And afterwards, so you will find out the matrix are quite different than before, because matrix before is like 16, and then 16, 16, and then 11, something like that. But right now you can see this proximity matrix is larger. Okay, and afterward, we utilize this proximity matrix, what we try to choose. Again, we're choosing the smallest one, and I'm hoping when I go through this step, you will likely to know that something is a little bit strange. Okay, I hope you can feel that way. And then afterward, we update our proximity matrix. It looks like this way. So then, remember the previous one? We say, because they all become 11, so then I randomly pick, right? Right now, there's no way for me to randomly pick. I only can pick C2 prompt with C1 to merge. So the next step, what I need to do is I'm merging these two. And here are my update proximity matrix. So it will look like right here, how I try to choose, what kind of strategy I choose to update my proximity matrix will affect the final cluster result, right? And then I try to see this comparison. The left-hand side is minimum 1. The right-hand side is maximum 1. Did you see some common strategy, right? Some characteristic right here? So if you actually go through the study by your own, that is why we say the minimum one, usually you will find out they will tend to have very large cluster, because you can see the left-hand side one, it looks like it's very large cluster. And maximum one usually will tend to somehow break the cluster to the smaller one. You see that example right here, right? And then let's try to see. Here is another example that's provided by our textbook. They try to show you the minimum, maximum, group average, and see what's going on. So at the very beginning, these two are merged. There, you will usually find out at the very beginning, when they're merging at the very beginning, they did not see much difference. Okay, and then after that, this is a second, still the same. At the very beginning, they're almost the same. It only changes when the cluster starting to merge. So then afterward, the third one, the group average merge with this thing. And the minimum one, the maximum one merge the same thing as the group average, but minimum one actually will find out the merging differently. And from that stage, you will find out the minimum, when you try to update your proximity based on the minimum one, and then they will usually try to merge in some cluster. It looks like it's a little bit far away. Why? Let's try to thinking about why. Because when the maximum, when you utilize maximum, okay, let us try to go back to right here. Why the maximum one actually merging these two? Because these two clusters, they will consider that is their distance. Okay, and then these two clusters, they will consider this is a distance. They utilize maximum one, but in the minimum one, how they will look like, that is their distance. Okay, and here are the distance, here are the distance. So in the end, it will feel like these two are quite similar. So how they update will changing the result later. Okay, and so then you continue on. If you see this one, you will find out in the end, they will look very different. The hierarchy will look very different. We don't know which one is the best strategy. I mean, in data mining, you will always find out that we don't really have an ideal case. We usually ask you guys to reason, because sometimes maybe in certain common standard, it looks like A, but if you can reason then, talking about why or what kind of pre-processing way you're going to do, and what kind of characteristic you want to emphasize, if they make sense, we will accept that too. Okay, so that is a comparison. Okay, we ask you to do more comparison, but right now, because I only show you the minimum maximum one, so we can tell you the strengths of the minimum one, because you can see the shape. Actually, they can handle non-eclipse shape. They actually merging in the very far away. But the limitation is they are sensitive to the noise and outlier. Why they are more sensitive to noise and outlier? Because you utilize minimum to select which one need to cluster. And then you're choosing the minimum. So you can imagine it's like they double the importance of the minimum. So if right now the noise in the minimal part, you actually become more sensitive, right? But why the maximum one are not that being affected by the noise and outlier as compared to minima. By the way, you need to know it's compared to that. Why is not that serious as compared to minima? Because you're choosing the minima and utilize maximum one. So you actually can find out it's kind of try to average things out during that process. If you're thinking about that, why the noise and outlier actually will make an impact if every time you utilize same strategy, and it will be likely to pulling through you to the very extreme case. Okay, but the minimum, maximum is like to force. And then if you're having the minimum, so you keep on go to the right direction. Assume the minimum is right direction. So minimum, utilize minimum to select the cluster and utilize minimum to actually update the proximity. It looks like you're always having the right force. And in the end, it will leading you out of the door because right now in my classroom, the door is on my right hand side. But the minimum maximum, the maximum one is more like the another force, like go to the left hand side. So I go the minimum one right hand side, and my maximum one pulling me back. So minimum go right, and the maximum pulling me back. So in the end, I will actually approaching to my door in the slower fashion as compared to utilize minima. Okay, so that is the part we want you to know. And then, but the maximum one, actually, we're thinking they are biased towards some global cluster, because then if they are too big and to this one, and then it's very wrong, and then maybe the maximum one usually will actually place them in the very different location, so it might not be good enough. Okay, so then we already go over for 40 minutes. Here is a class lottery, and then the.
忘记开这个 Basecamp。
Won't you have Basecamp? Okay. So the answer for the class lottery is BB scan. You know why it's called BB scan? Because that is the most important concept for today. Nice. 应该是这台的 camera 没有被取代，以前都是 laptop。
哦。
So TA find out that my face did not show up. Oh, by the way, I would like to let you know that I told the TA this week we will try to find different way to put the caption into our after produced things, and then we are not going to put the caption on the video, and then we will try to put the caption title embed in the YouTube. So you can decide to turn on or turn off. And then if that is possible, then I will make different TA to make that caption to translate into Mandarin. So then you can turn on Mandarin or turn on English to see if that is possible. I'm sorry, I did not think about that strategy before. I just thought about that last week. 还是开不起来的，开起来了，所以好了吗？有了。没有，就是 laptop 对，可以。So if you are in class, remember to go to the whiteboard to take a shot on that. 你们比较晚进来的，要记得到白板来拍那个白板上的那个 QR code。3分钟，快到了，快！OK， 你可以走近一点，反正没有人看得到你。我看得到啦，线上的人看不到。Sorry, I'm talking to him, saying no one can actually see you. Can actually go nearby. Okay, so we are going to go to the concept. called density-based clustering. Okay, I think that is the most important concept for today. Okay, so why we want to go to the density-based clustering is because you know the K-mean, DOD, and so many things, they actually like the distance, they like the cluster that the distance are short from the mean, from the representative to the point, okay? And then what is the shortest? So this one will be okay, right? Because then for every point, so this one has some center, and then right here, actually you having the same distance, almost the same distance. So it will be likely to group them together, okay? And that, but you can actually find out sometimes our cluster are not in this round shape. For example, here is one cluster. From human's eye, you know that this supposedly should be belong to 1. But if you utilize K-mean, they definitely will be break up to the smaller parts. They will not be grouped together. So the researcher tried so many ways to thinking about how I actually would be able to connect between them. So the clustering mechanism actually try to handle that kind of shape. It's called density-based cluster. Why we call them density-based cluster is because there's one very important concept called density. It's a key concept. The K-mean, K-mean-OD, you can actually thinking about they clustering based on distance. Okay? But density-based clustering based on density. Okay, so each cluster has some criteria. Then I try to go through. There are so many different density-based clusters, but I'm not going to talking about all of them. We want to starting from the very, even though it's published earlier, but that's very popular in the density-based cluster. The remaining part of them are just like improvement of it. So let's try to see what does that mean. Okay, DV scan, the D maybe stand for density, I think, but they were trying to scan through things. Okay, and so what is density? Density is within some range. You're just thinking about that. Within certain range, how many points within that range? So that's try to, we actually have different points, but I don't want to go through that. Let me try to utilize the illustration first. Okay, so in a DB scan, they have two major concepts. One is how many numbers. So how many number right here is called minimum points. So assuming right now I say within certain range, you need to have at least 4 points to satisfy that density. So the 4 right now minimum point is like the number of the point right here. So what is EPS? EPS you can imagine, so for example, is a radius from the point to certain border. So for example, right now, you can actually see this EPS right now. I have some radius, right? And this radius, I actually see from my point of it. So for example, here, I have a point. This is a point. And assume my EPS, my radius, is this much. So 1 actually is mean from my side, I use this radius to draw a circle around me. So remember, density-based cluster is they actually make every point become a center of the circle. And see who are nearby, how many points are nearby. So like this point right now, how many people are nearby within that radius? 1, 2, 3, 4, 5, 6. 6 points. Okay, so if you actually the number of the points surround you within this radius, okay, if that number is higher than the minimum point, because right now I say there are 6, right? and the minimum point is 4. If they're higher than that threshold, I will name this point a core point. So you actually will find out right now, we mentioned certain thing called core point. Core points are the point, actually they have more than the minimum point that is supposed to have. That is what is called core point. Okay, so in that cases, let me try to. Okay, so then this have many, so you can let me try to make them as a core point. Make them become red color. So I actually can scan the whole database. Utilize the radius to scan for all the points, and then afterward, I will find so many core points, right? But here there's another example. I utilize the radius, and then this is the center, and then I go through them. And I find out this point only has 3 neighbors. 1, 2, 3. You can see 1, 2, 3. So it's less than 4. But this point, actually one of its neighbors are core point. Right? You can actually see the core point, the red points right here. So then we will call this point a border point. They are okay. I think they are important because they are neighbor of the core. So if they are core or neighbor of the core, which means they are important, I would like to take care of that. Okay. So if no problem, so then let's try to see with this one. Assume this is the example. This point actually have only 2 points, but they do not actually have become the neighbor of any core point. In that case, I make them become noise point. So all the information that we try to talking about right here, you can actually see the definition we illustrate right here in this example. So first you could, and afterward, I will having those points. Core point marked as red, border point marked as blue, and noise point marked as green. So far so good? Fine? So next one we want to working with, so see right here, here are the algorithm for the DB scan. The DB scan actually will say, let me try to go through them. First, they will eliminate the noise point. I call them noise, which means I don't want to care about that. So that's first thing. The second thing, you will find out there's a for loop. For loop right here. That is a for loop. And loop about what? Loop about all the core points. Okay? The remaining part, I don't want to read right here because you got sleepy. So let me try to utilize illustration to go through. First, we eliminate all the noise points. Right? Then afterward, we go for every core point one by one, assuming the first core point I select is this one. This is my first point. And then there's no any other core points being visited. So then right now, I give a name to this core point. Let me try to name them as cluster 1. So then I name it as this core point as cluster 1. All the neighbors of this core point will get the same name, cluster 1. So far so good? Okay, so remember that illustration because if you go back to the algorithm, they just fit what it meant. And afterward, we're done with this one, right? Because all the core point, what he knows is about the neighbor. So all my neighbors belong to me. Hey, you guys actually are giving you the same flag. And afterward, I'm moving to the next core point. So remember the for loop is go for the core point, right? So I look to the next core point. So assume this is the next core point I try to go through. And because my core point already got a flag called cluster 1. So what I did is I utilized the same flag to attach to my neighbor. So you can imagine it's more like a virus, don't you feel? The core point actually have a virus, and then make all the neighbor actually get poison or get sick because of that. And then the same virus actually will be propagate to other clusters. So then the next call point actually say right now, because one of my neighbor are not being contagious, not being get this virus yet, so let me try to make them as a neighbor one. So I go through them one by one, and then afterward, assuming I go to the next call point, and so all the call point I already visit, and then next one I go to this call point, and then you find out this call point got no any virus at all. I mean, they do not having any tag. So then right now I start one thing new. So I named myself as cluster 2. So far so good. So you can imagine what I did is I go for every call point. If the call point do not having a label, I print a mark right here. Then I propagate the mark to all my neighbor and go to the next one and go to the next one. So then afterward you will find out all the neighbor actually is marked as a 2, and then we go for the next one 2. So in the end of the loop, then you will find out that my cluster, I have 2 clusters. So in these cases, you will see I don't need K, means K. Because I just go for every call point, and in the end, when the thing's being done, you will know how many clusters you have. So what is a cluster would look like? In this example, you get one cluster right here, another cluster right here. See? Very different shape. Okay, so that is how the DB scan works. So far so good? And then here is the example when the DB scan, so for example, origin point is left-hand side, and then afterward, if you say the EPS equal to 10, in that example, minimum point is equal to 4, and then they try to show you the different kind of core point, and then the border point, and noise point. So when that work well, and you will get something like that. If they did not work well, you will get something different. So then, it's done my talking, it will be your time to do this practice. Go to the NTU Cool and try to see what are the advantage of the DB scan or drawback of DB scan. How many people online?
我们那个 paper presentation 已经都公告了，对不对？对，公告了。啊，分组也都分了哈。
Do you guys all finish or who haven't finished? Okay. 教室都完成了是不是 Who haven't finished? You all finished, right? Okay, because TA tell me there are 45 people online, and then count we have around 20 people. Okay, so you know the ratio. Okay, so let's see what is the primary principle behind the DB-SCAN clustering. Okay, and there are some answers usually they are not right. So for example, DB-SCAN do not really relate to centroid. No, it's related to density. So cluster depend on distance between the farthest point. No, that is not. So the first two, actually they are not. You need to know what is the important keyword. And then the third one also is not, because it's not based on a hierarchical relationship. If you actually make this one wrong, I don't know what happened. Probably it's because you did not really listen to me, I think. Or actually you don't care, so just click, done. Okay, so if you are the later one, you say because I don't care, it did not count, then it's fine. But then if you are the one who really pay attention to it, you need to know why those answers are not that accurate. So the clusters are created by detecting the region of the dense data point. You will find out they're having the keyword called dense. Okay, which one of the following, let me try to refresh again to see if there's, okay. So then, don't know why those people, okay, fine. So which of the following are characteristic of the DB-SCAN? Characteristic of DB-SCAN, because it's a multiple select question. First, it required a number of the cluster to be specified in advance. No, it did not. Only K-mean only need that. DB-SCAN do not need this one, so it is not. You can identify the cluster of arbitrary shape. That is correct. You can see that the different shape we can do. It is not influenced by the order of the data point. Yes, it did not. You can actually see the cluster is actually, some people might say, no, I think it will influence because we go to the different core point one by one. But you can imagine, unless you only emphasize on what? On the, if you so pay attention to the cluster number, so the order of the data point, how I try to scan through them, and they will only affect the cluster number. Because right now, sometimes you go from the right-hand side, and then the right-hand side actually have the cluster 1, and then go to the left-hand side 1, they become cluster 5. But if you start from the left-hand side 1, the cluster actually is 1, and then go to the right-hand side was 5. So only difference is only the cluster number. But in clustering mechanism, we don't care about the cluster number. So that is why we say it's not influenced by order of the data point. Okay, so if you get confused right here, let me try to clarify them for you. Okay, so the last part, it can effectively handle data set with cluster or varying density. It's wrong, because you can imagine, right now we're only talking about one type of a density. Within this radius, how many points right here? So it's only one matrix. Okay, if you actually changing the different number of the point, or the region, you will find out you get totally different result. So it cannot handle the different density at the same time. No, it cannot. Okay, so you need to know the last part, because you might find out that you see the density, but you need to know dB scan can only handle one type of the density. Okay, so match the following term to their appropriate description. The first, a point that does not belong to any cluster and is not sufficient close to other point. So it's not core, and that do not close to any other one, that will be called noise point. Okay, the next one. The minimum number of the point required to form a dense region, that is the minimum point that we try to talking about. And the point that has fewer than minimum point with epsilon, so the epsilon is epsilon distance, but it is in the neighbor of the core point, that is called border point. A radius that determines the neighbor around a point, so that's called the epsilon. So this EPS that we're talking about. So if you're looking for the EPS, you did not find, apologize, epsilon. And the point that has at least minimum point within its epsilon neighbor, that is the core point. Okay, so the last one. There are two major reasons the dB scan cannot work well. One is if you have different kind of density, and another is high dimensional data. So the following figure could not cluster well because of what? You can actually see so many different density. So that is why they cannot cluster well. So here are the very density. We usually will not have the question about high dimensionality data. You know why? Because it's difficult for us to illustrate. Haha. Okay. When we illustrate, we can only illustrate the 2-dimension or 3-dimension at most. Okay, I hope by that you studied more. The next one, how we try to determine the EPS and minimum point. You will find out the same strategy. Actually, we utilize that a lot. Previously, we're talking about elbow point. Actually, right now, you will also find out, we try to find the elbow point right here. We try to, ideal is like try to go through, try many different distance, and then find out which one is a better elbow point that we try to looking for. Okay, so that is basically the idea right here. But because this morning we already mentioned about that, that is why I don't want to emphasize on that. Okay, so next one, how you guys find? So next one we are going to talking about another concept called shared nearest neighbor approach. Why we want to talking about shared nearest neighbor approach? Because we want to take care of various density problem. Okay, but you will find out the shared nearest neighbor approach also been mentioned a lot in different concepts. Before that, before I go on, let me try to stop right here a little bit. Try to thinking about what kind of shared nearest neighbor approach that we also mentioned before we tried to talking about clustering. Anyone remember? I think I go through things very quickly in the classification. One concept we call about is called K nearest neighbor. Do you guys remember? I think I mentioned, but it's a very quick version. I'm apologize for that. And then K nearest neighbor, what it meant is you can imagine the dB scan is also more like K nearest neighbor, right? I have this radius, but then it is not K nearest neighbor. It's just like the neighbor within the radius. So they don't have the K. Okay, but then right here, you can imagine the illustration right now. We already give you some concept called K nearest neighbor. Why? Because sometimes I don't know how many K. So the number of the point actually is a K we're talking about. Right? The K that we're talking about. So right here, they want to looking for what is the best K. So right now, so here, the fourth nearest neighbor, okay, and then I try to looking for the distance, and then I find, so then how many points actually have in that perspective. So nearest neighbor actually is a very important concept in our real life. There's one study, I forgot, no, it's not forgot. I intentionally not to reveal that because it's not directly related to this course. It's related to other data mining course. There's one, I did not have in my slide, so I can only say in a story way. Okay, there's one medical research. They try to study 20 or 30 years. I remember, Sergey, you probably know, we mentioned that in the social network thing. And they try to study the people and then looking for all the characteristics, all the factors that may affect their health. And then they try to, so for example, the gender, the family history, and then the friend, and then see many things. So they study that for many, many years, like 20 or 30 years. And then afterward, for every factor, they plot the correlation, like how this factor related to, so for example, weight, overweight. If you can imagine, overweight is a very important criteria. So then let me ask you one thing. So then if I want to estimate or like want to predict who were likely to be overweight based on some information about that person. One is about his DNA. The first one, assume that's DNA. The second one is like his wife or husband. Okay, and then the third one actually based on the friend. And the fourth one based on the friends of friends. And then, or the fifth one based on sibling, brother or sister. Okay, so right now, assume I want to predict what a person being overweight based on 1, 2, 3, 4, 5. Which one you are going to choose? So let me do these things. Go to slide 2. No. Go to the wrong one. This is the wrong one, sorry. Sorry, we didn't go to the wrong one.
那个是上次的，没关系，没关系，没关系。
The private Keiko competition was cancelled and it doesn't seem to work. I don't know. I will make the TA to check. I don't know which private Keiko competition you're talking about. What? Oh, Lab 2. So is Lab 2 cancelled? I will ask the TA to extend the time. Some people probably were late for the homework, so they're adding. So let me try to add in a question, multiple question right here. What did I say? DNA and then wife, husband, friend or friend, brother and sister. One less is what? What? I forget. I say that and forget. Brother, sister. Okay. stop and slide to think allow you to go to. So try to click which one you think. That probably will affect. That's your weight. Which factor you think will affect? DNA, friend, husband and wife, friend, brother and sister, friend or friend. Let's see how many people try to vote. It's a very interesting study. When I see the study, I'm just like, ha, ha, ha. So fun. But you need to know, I'm talking about this one because we're talking about nearest neighbor, right? So many people think that is DNA. You bring everything to DNA. Okay, so there we have 52 people try to do the NTU Cooled quiz. So let me try to wait. I guess most people already vote. Okay, and then clearly right now that the people actually the top 3 factor you think actually play a most important part will be the DNA, about the friend, about wife and husband, and about like the friend of friend actually is this, and no one blame the brother and sister. Good. So it looks like you guys know that the brother and sister actually, oh, some people, after I say that no one blame the brother and sister, and they did. Okay, how do I do full screen? Right here. That is the answer that you vote. Interesting thing actually is in that study, they try to correlate the different factor with the overweight thing. And the highest factor, so the one have the highest correlation, is a friend of the friend. Ha ha ha! You got shocked, right? I got shocked too. Okay, and then after that, I was thinking about that. I said, oh, it makes sense. Why? Because if your friends of one are very heavy, your friends of a friend are very heavy, you are likely to be very heavy too. Because they are talking about the living pattern. So flock or bird, you usually will try to eating with the same people, I guess. So you can imagine that is in that study. They say, okay, if you can actually estimate another person's eating pattern by his friends or friend, because if the friend actually is quite correlate quite a lot, but then the friend of friend actually have highest boost, and it's DNA actually affect a little bit, but not as important as a friend of friend. Okay, so friend of friend means that you having the same eating pattern. In the study, that's what they say. Okay, and then the reason we try to mention about that is because you can see that in our DB scan, when we try to do the core point, and then we try to have another core point, and then the border point between the core point to another core point is more like a friend of friend. Okay, actually, the core point is the friend of the border point of the friend for that core point. So somehow it actually is really related. So the neighbor actually is quite related. And then in our nearest neighbor, so for example, in the online recommendation system, they also utilize the friend. But when they're talking about friend, it's not really real friend. It's about the people are likely to having the same similar interests you have. Okay, if you are having the similar interests, you are likely to purchase the same thing together. So that is the concept of the nearest neighbor. Okay, so I'm glad that you guys try to working these things with me. Thank you. And then for the people who have the question about the private Kaggle competition, I think we do not cancel. Probably just the time was up, and I will ask the TA to open up the Kaggle competition time. Okay. I remember last year they told me they have a certain issue about that. So if you are late, they might need to give you the different link based on my last year's experience. Okay, so right now we already mentioned that the neighbor actually is quite important because how much you share actually will strengthen the understanding about the concept. In that cases, share nearest neighbor approach would like to construct a graph called share nearest neighbor graph. So in that graph, there are weights between one point to another point. It's not just based on their distance. It's based on how many shared neighbors they have. So for example, you can see in this illustration, I and J are actually linked right now. But I and J, we actually will say also, so I actually link to, so assume they are A, B, C, D. I also link to A, J also link to A, and I link to B, J also link to B, I link to C, J link to C, etc. So in that cases, because they share 4 neighbors, so my weight supposedly should be 4. So in the share nearest neighbor approach, they pay attention to who are the same neighbor. So far so good? So I'm going to talking about share nearest neighbor approach because they say after you adopt this concept into DBSCAN, that the various density problem can be solved. Okay, so let me illustrate how they try to work with it. By the way, if you find out your handout are completely different than mine, I did, and it's because I changed yesterday. Okay, so first they try to compute proximity matrix, but right now I just assume they are similarity matrix. And this matrix, again, because you will find out we keep utilize different term. And this similarity matrix, we just say we try to store the similar value between the pair. And then afterward, we will try to sparsify the similarity matrix. Okay, so that's try to talking about how we try to, what do we mean by sparsify the similarity matrix? So first, I have the similarity matrix just like that. Assume that is my similarity matrix, okay? And then the higher the value, the better. So because, which means they are important. And when I say sparsify the similarity matrix, is I don't want to keep so many value on my matrix. I want to only keep the k most similar neighbor. In that cases, I probably just keep the k equal to 5. So right now you can see originally this matrix very big, and I keep only 5, so many value actually just delete. So far so good? So that is called sparsify the similarity matrix. Okay, and then afterward, what I did is I sparsify, so we already done with the first one and first 2. The third one, we try to construct the share nearest neighbor graph. So from that matrix, what does that mean? Okay, so let me try to show the example. So here is the example. I actually having those value. I construct the similarity matrix. Assume that's the step 1 that we try to talking about. And then afterward, I try to do the sparsify. So I say right now 5 most similar neighbor. And then I cut them out to this one. So that part we're already talking about. The next step is we try to construct the graph. Okay, so that is a graph we try to construct. We make them to have the age. So far so good? Okay, and after they have the age, I will know that who are the corresponding neighbor and then given the weight. So that is the tricky part I would like to talking about. So for example, right now, 1 and 2, I want to know the weights on the graph. So what should I do? I try to see how many neighbor I have, common neighbor, shared neighbor I have. So you can actually see the point 1 and point 2, they have 1, they are similar neighbor, right? Because if you have the value, which means they are similar. So 1, 2, 3, right? Because the remaining of them are not the common neighbor, because like 1 have 5 as a neighbor, but 2 do not have 5. And 2 have 7 as a neighbor, but then it is not on this one. So then you can find out the common neighbor I have is only 3. So in that cases, I place 3 right here in my weight. So step 4 is try to place the weight. So far so good? Fine? Are you guys, do I need to go to the illustration again?
Yes.
Okay, so this part so far so good, this one is fine? Okay, because we have the matrix and only keep the 5 for every element. And then after that, based on every 5 right here, I can construct a graph. So far so good? So how the graph we construct? For example, 1 linked to 2, 1 linked to 3, 1 linked to 4, 1 linked to 5, 1 linked to 6, something like that. So you see the value on the similarity matrix. I place a weight. So far so good. And then afterward, my graph actually need to have my age, because right now, right here, so you can see there are so many age on that graph, and I need to place weight. Okay. So the weight is not 1, 1, 1. The weight is about how many shared neighbor between these 2 points. Understand the thing I'm talking about? I want to have a weight. Weight are how many shared neighbor I have. So in that example, I try to see 1 and 2. By the way, we need to do the same thing for all the weight. I just don't want to go for so many age right here. Just try to give you an example. Assume I want to find the weights between 1 and 2. What is the weight for 1 and 2? You actually pay attention to this row, right? Because that is about who are the neighbor of 1, and who are neighbor of the 2. So far so good? And then afterward, I see how many points actually are the neighbor of 1 and the neighbor of the 2 together at the same time. So that is why I have 3 circles. 1 have 3 as a neighbor, 2 also have 3 as a neighbor. Okay, so that's 1. 1 have 4 as a neighbor, 2 also have 4 as a neighbor. That's another 1. Okay, and then after that, 5 do not, because you do not see the 5 in the 2, but 6 have that in 1, 6 also a neighbor of the 2, so then 3. So because then after that, we go to 1, 2, 3, 4, 5, 6, 7, and we find out 3, so then I will have 3 as a weight for 1 to 2. We can do the same thing for 2 to 3. We can do the same thing for 2 to 3. So for example, 2 and 3 right here, let's try to pay attention to 2 and 3. 2 and 3 have a neighbor called 1. 2 and 3 have the common neighbor called 4. 2 and 3 have the common neighbor called 6. Then we have that 3. We can do the same thing over and over for the whole entire graph. So far so good? Okay, so if that is clear, then I try to go to check this one. So that is what we did. So we do 1, 2, 3, 4, right? We actually find the density. So right here, we try to say how many neighbor that we have. So that's try to have a very short summary between the dbSCAN to SNN, because there's a big difference between these two. dbSCAN, what is the density? Density is like how many points given around the given point within the specified radius. Okay, SNN changing the density. Okay, changing the density by how many nearest neighbor around me, k nearest neighbor. So you actually can see 5, something like that. And then we want to show you the weight right here because it's a very easy way to talking about, try to calculate. So you can, they have 2 different versions I've been seeing. The first one that we did not talking about, this one is a version that we calculate. The second one is the one we try to calculate. It goes easier. We try to talking about the number of points within that radius, within that k, and then we actually say that is 3 or 4. So that is the weight that we're talking about. Okay, so that is density. All the weight actually in the end plays the density, become the density right here that we're talking about. And after that, so 1, 2, 3, 4, we finish. Then how about 5, 6, 7, 8? They say actually 5, 6, 7, 8 are just dB scan. Once you're changing the densities definition, you continue to utilize dB scan to find the core point and then try to form the cluster based on the core point and discard all the points, something like that. So that is done with the SNN. Okay, so how about you thinking for a while and that's have our class lottery and after. Okay, so it's 10:40. Okay, and here are some questions and from the student, and I think we kind of already addressed that. The deadline for this one, we will go back to check with it. Okay, so can you upload the latest version of the slide to NTU Cool? I think first, I did not guarantee the handout actually are complete. So then, some of the example usually will also do not having them. So then, if you want to know there's some new version you want to go with it, how about you try to do the screenshot by yourself? I don't think I can actually check which one actually I update because I update the slide every week. Okay, so if you want to get this one, go to the screenshot. Okay, so can we see a short example of SNN dB scan? Unfortunately, I do not prepare for it. But I actually noticed some people have the question and during the break. So I was thinking about, because you need to know the generate the example really are time consuming. So sometimes I just go over first. So imagine the SNN, we try to show you this different step, right? Step 1, step 2, step 3, and step 4. Okay, so after you finish with this one, like 1 to 2, you having tried to calculate the weight, like 3 and 4, okay, that become your density. Okay, so what does it mean? Because the density actually from the dB scan is you actually were having a radius, so density from the dB scan is you have a radius, and then it's you, and then right here in the middle, and then you see how many points within it. So for example, if that's a 3, you keep a 3. So you can imagine this SNN similarity in the end, you're going to having some information like this is 2, this is 3, something like that. Right? And afterward, that you try to talking about the next things that we're talking about is you try to find out who are the core point. The core point actually is decided by your density. Understand about that? Because before it's actually, how do I know this core point? I try to see this radius and how many points within is, and then if you satisfy with that, you are core point. So you can imagine this density right now actually will become one of the features you are going to have to make you become core or border or noise. So far so good? Understand? So then afterward, the one who having the many common friends will likely to become the core point. Right? The one do not having so many mutual friends are likely to become noise or border point. So the remaining part, that is why we did not having the animation, are the same. Because once you're a core point, you're a border point or a noise point, actually just make you to to actually know how to link to the different clusters. So for the reservoir, actually you can thinking about go back to the DBSCAN right here that we're talking about. So after you need to know that you know it's a copoint and do the exact thing, and then try to see are you having the cluster label. If not, then you try to play this one and on that. So the reservoir is the same thing as a DBSCAN. So particularly, so I'm sorry because I do not actually prepare a slide for it, but because I thought the remaining part is quite similar, that's why I did not prepare. But if you really need that, come to take the course next year. I will prepare for it. I will remember that next year, but then unfortunately this year we did not prepare for it. Okay, there's some good question from the student. Some student actually say, Professor, actually when you try to draw this one during a break, and then I actually draw a shape look like that. So then the student asking, does that shape matter? So can I utilize that boundary? And later on, if I'm having a point, so input right here, and because within this boundary, and then we directly say, no, we don't actually, in the DBSCAN, we don't do something like that. In DBSCAN, we don't. But you can imagine that is a good way for you without reprocess the clustering and do something in the middle, but it is not called DBSCAN. Okay, clustering is every time you have to input the data, and then you do the clustering and get one output. But until you do the next clustering, you might say, but they having some middle point come in. Which cluster they belong to? That could be a strategy that you can use, but that do not belong to DBSCAN. DBSCAN only give you the one shot, and after one shot, how you try to maintain on your own. Okay, so then how the shape coming out, maybe it's another research. Okay, maybe it's another research. And then there's one interesting part I would like to say about the shared nearest neighbor approach. If you actually go through this process, this 1, 2, 3, 4 process, and then afterward you understand about them, and then go to another process right here, and then 5, 6, 7, 8, we told you that is DBSCAN. Then you might say, wait, if the DBSCAN is a method, can I consider this 1, 2, 3, 4 as a pre-processing? You could, right? So you will find out a lot of technique that right now, no matter in machine learning or data mining part, you'll find out sometimes they will having some core technique. They are the same. But then how they try to describe the method, update the method, then you can, some people consider that they're just called pre-processing. Some people make a deal and to embed that and to produce a new method. So how to package is a skill too, right? If you do not package things well, then you just call them pre-processing. You are not going to having something called SNN. Do you get it? 要懂得卖东西，同学们，在台湾的同学都不太懂得卖东西。有的时候不要说它只是一个，所以没什么，不是。You package them, they become another technique. So I would like to show this one to you too. Okay, how to sell is an important skill too. Okay, and sometimes certain very interesting pre-processing actually is worth to mention and to share with other people. Okay, so then here is the SNN thing they're talking about. If you utilize a different density and the high density and low density and medium density, how it would look like. And by utilize the SNN before, the SNN density, this kind of revising, and they were able to show that you can see to partition different clusters right here. So that is the part they try to say, okay, once you consider mutual or like common friend between each other, and then changing your density definition a little bit, and the drawback of the DBSCAN can be changed. Okay, so then try to go to this practice to see how the overcoming the DBSCAN limit with SNN, and try to understand more from that. Oh, by the way, they do having some student keep saying that, can we actually, see the sample data, sample exam question, okay? And in the last week, the TA already sent announcement and give you the sample questions. If you cannot find it out, you can actually see there's a module and talking about final exam in December 8th. And a few days before, we are going to ask you to do some testing from the people not in the Tsinghua. In the Tsinghua people, you don't need to care about it because just come to the classroom and having the paper, we will deliver them. But if you are outside the Tsinghua, then you need to know how to practice to upload the file to the NTU Cool, okay? So all the answer and outside the Tsinghua, you need to upload to NTU Cool. And another thing is if you are the school nearby, so in other words, you are National Yangming Jiao Tong University, especially you are belong to Jiao Tong University campus, then we will suggest you to take the exam right here in Tsinghua. But we are going to do a survey with you, okay? And in the exam time, we will partition you guys into 2 different classrooms. One here is here, another one is in 106. So our TA, we're having a seat map for you. Okay, so that is about the final exam. So you can take the courses next year then to get the short thing. Okay, no, or you can come next time. I'm sorry that this year we did not prepare for it. Well done. You haven't finished? Well done, right? Okay, so then the first part, I think we already mentioned. This one is just a reminder. It actually is a DBSCAN actually having a problem that the very density problem cannot be solved. So then that is, here this example try to show the density problem, okay, just like the previous one. I'm very curious because we already have this question in the previous one, and we say that should be density. When we go to this one, we're still having the people say that is high dimension. Why? Okay. Interesting. Okay, so and then this part, supposedly it should be a scalar. I don't think that will be having a totally correct answer. It's just for you to know that from my perspective how likely it is. So for example, some people think that it's highly related, somehow people say that it's somehow related, but if you have your own reason, changing the scale a little bit, I don't think that matters. So don't feel sad because you do not choosing the same thing. The part is if I actually say it's highly related, but you're choosing unrelated, that part is concern. But if that's something somehow to highly, that part, that can be argued. So the first one, compute the similarity matrix. Somehow I think it's related to high dimensional issue because when you compute the similarity matrix, you don't need to recompute it again. So they are related. But how much is related? From me, I think it's just somehow related. But you probably will say that's the most important part. I will not going to argue with it. So next one, try to specify the similarity. I think specify one really reduce the thing about high dimensionality, because then you don't need to do so many computation. You just actually right from now, you only pay attention to the number, the k number that you try to pay attention to. So that are really, from my perspective, I think specified are more related. Okay, and construct the shared nearest neighbor graph from specified matrix. That is a way they try to working with for the density. But I will not argue say it could be solving the problem of high dimensionality. So I did not directly say they are totally not. Okay, find the density of each point is not really related to high dimensional issue. Okay, the part of them actually supposedly in Google form, if I would do that, it will be totally in one question. Unfortunately, that's because in the NT-CoolWorld, so we need to separate into the two different reasons. Because one is density, one is high dimensionality. So how about the density part? Compute the similarity matrix is somehow related. You will find out that all the things that we're talking about are somehow related, but just depends on which one are highly related, which one are not highly related. So specify, I think, is also related. And construct the shared nearest neighbor graph, I think is highly related. And find the SNN density for each point, because then we consider the shared neighbor and then become various density. So that is somehow high related. Okay, so that is a part for you to think more about that. But if your answer between the somehow and highly, you are a little bit different from my perspective, I think it's totally fine. Okay, so then next one, then we try to go to the cluster validation. You'll find out that I have many slides right here today, don't worry. And cluster validation, there are a few points that we want to emphasize. Okay, first, because clusters do not having their own answer. So how good they are hard to tell, really hard to tell. But we do having some tendency, okay, utilize certain metrics to somehow evaluate the tendency. Why we say it's hard to tell? For example, if we generate a random data, just like what we try to show right here, okay, and then we send that to cluster mechanism, and the cluster mechanism go to the k-mean, they probably will tell you that if your k equal to 3, they are going to show you those clusters. If they go to the DB-scan, they are going to show you that cluster. And go to the completely, do the augmented one, they were going to show you this one. Are they wrong? They are fine, right? Even though they are totally random, I think they are not really related to cluster when I generate. But it will somehow give you certain concept. Just like, do you guys having the experience? Like yesterday, I actually see the sky and see the cloud. We tell there's a ship. I mean, have you had the experience? No one has the experience? You look at the sky and see the cloud. And say, there's a whale right here. There's a dog. I mean, does the cloud actually want to make them as a dog? No. It just looks like a dog to you. Okay? Cluster is something like that. They don't, all the data did not say it has to be here and that. But then after you go to the cluster, they were going to give you some meaning. Maybe you do not know that before, just like when you look at the sky. Okay, so they have different aspects when we try to do the validation. One important keyword is called tendency. Okay, so that is the way how we try to evaluate how good they are. We base on the tendency. Okay, and then this part, the 2, 3, 4, 5, is the one that you can go back to looking at it. We will try to give you the example one by one. Okay, the first one, we actually try to go for a different perspective. Okay, so for example, we actually can utilize external index. What is the external index? Is assume you already can find some class label. It is not, you do not utilize that as a supervised classification, but you utilize the classification label as something to guide the clustering. That is possible too. I'm going to show you the example later on if this part you do not understand, but just know external index is you already having some concept. That kind of concept, maybe for example, you know like 20% of the concept. Okay, 80% of them you do not know their answer. You do not know. So if I only utilize 20% of the data to the classification, it's too dangerous because you might actually did not guide them. So what we can do is we can actually mixing 80% with 20% into 100% and do the clustering. Okay, we can do the clustering. After clustering, then I know some data are within that cluster, and then I pick the 20% and then utilize that and say, see, supposedly that 20% is the one I know. These two belong to the same class. That two belong to the same class. That try to see does the cluster are actually having that perspective or not. Then you can utilize that as an external index. So far so good? Understand? Okay, good. So the internal index is something like we mentioned a lot in the clustering mechanism, like square sum of square error. Okay, we try to see how is the radius things right here. Or actually we can have certain relative index. We try to compare two different clusters, how relative they are. So there are 3 different approaches that we can do. But sometimes you will find out those clusters, some of way, sometimes they will probably bias toward to some of the technique. So let's try to see this first. Let's try to utilize one of the approaches called correlation. In that correlation, again, that is some slide I remade yesterday. One of the metrics, we call them proximity metrics. So assume right now I utilize similarity value. So here are proximity metrics, okay, that we tried to show you before. And then we can have in certain thing we call incidence matrix. What it means is like it's a cluster membership matrix. So assuming, based on the previous example we show you how to do the hierarchy clustering, in the end we know that C1 actually do not cluster with any other cluster. But C2, actually C2, C3, C4, C5 actually being clustered together. Assume if that is the cases. So then you can see this incident matrix right here. 1 represent that C2 actually in the end cluster with C3 in the same cluster. Okay, C1 and C3 actually C0, which means they are not in the same cluster. So that is called incident matrix. So you can have something try to show you the similarity matrix, like proximity matrix like that. You can have this incident matrix, and afterward, we calculate the correlation between them. That, I don't tell you how to do the correlation because I think we mentioned about correlation in the data part. Just send that to your statistic computation library, and then do that, try to do the compare. This matrix, you can find out that if they are similar or what is the correlation. If the high correlation, which means maybe they are good together. But if your incidence matrix and your presumptive matrix did not have high correlation, which means that maybe you did not do that well. So that is one way to utilize correlation to measure how good your cluster are. So far so good? Okay. Go to the next one. Oh, by the way, sorry for that. So this is not a good measure for DB scan. All the density-based ones are not good because they are more prefer this round shape. Okay, so this measurement are not good for DB scan and SMN. Okay, so here are some examples. Once we working with this example, go back to this random one. So for example, in the random data, we probably were able to find the correlation is the right-hand side one, and the left-hand side one, we will find our correlation is higher. So this one demonstrates we can utilize correlation to indicate how good the cluster are. Okay? So next one, we can utilize sum of square error. This part, I think I already mentioned, this is elbow one that we try to talking about. So for example, this is how many K we're going to have, and this is the y-axis is the sum of square error. Then you will find out the best way for you to have the K is 10, because there's an elbow. If you do not like 10, you can do 5. 5 is also a nice one. Okay, so then it actually can show from your information. So that is an internal measure that we try to talking about. Utilize sum of a square error. In that cases, I don't need to pay attention to any class label. Okay, so then internal measure, actually they have two parts that we try to talking about. One is called cluster cohesion. Cohesion means how close they are, how much you want to put them together. That is called cohesion. And separation is how separate they are. So most of the time, actually, you can imagine, I can do sum of square error, but then if I do sum of square error within the cluster, okay, within the cluster itself, that is called cluster cohesion. And then if I do the sum of square error between the different cluster, that is called cluster separation. So even though there are sum of square error, I can utilize that within the same cluster or actually in the different cluster. And then we try to see how good, so for example, they do having some other measurements say, I actually can having the cluster cohesion and cluster separation because A is cluster cohesion, B is cluster separation. Then I can utilize certain ways like this one, to estimate how good they are. If they are closer to 1, the better. Do you know why the closer to 1 is better? Because which means B is very far away. If B is very far away, this one is closer to 0, and there is 1. So we want A is smaller as possible, B is as big as possible. So then that is called silhouette coefficient. Some people actually try to, if you do not understand what I meant, you're just thinking about that is a way they try to utilize cohesion, separation, and do the divide and to get the value. Okay, I don't think there's some standard way to say which one is the best. Sometimes totally depends. Okay, so next one is our last anti-cool practice. I hope you can see the illusion. They having some figure that you can see. if you find out your answer about likely or not likely, very likely is very different from me, don't feel upset, okay? I think it's just some practice. From my perspective, I think the most important part for this quiz in the classroom is for you to exercise your brain. So if you do not exercise your brain, you just click and finish that. I feel like it's a waste because you did not really make your memory to, do not make your brain muscle to work. It's quite a biggie. But then, so the matter is not how likely you get the answer correct or not. Okay, I think most people already done, right? I see the 35. First, I would like to know that I would like you to know that marker illusion actually, except me, probably no one actually tried to put these two concepts into the clustering mechanism with me. So in other words, there's no standard answer. Okay, I just feel it's interesting for you to know. Okay, and why it's interesting for you to know is because you can actually see that how we perceive actually how about we perceive this object somehow is related to the information nearby. That is the concept we want to talking about. And then why this illusion somehow might be related to clustering, because clustering do not have a standard answer. Clustering actually is based on the surrounding based on information. So it would be likely that's because the surrounding actually is a wrong surrounding, it's a noise surrounding. It might affect how you feel about it. So when I actually try to generate this question and this Munger illusion, I was thinking about noise. I am thinking about noise. But if you do not thinking the noise, you are thinking about something else, then it will be very possible you will have the different answers compared to me. So don't get upset. Just like I say, if there's something like likely or somehow likely and very likely, your skill is a little bit different than me, then it's fine. But if there's something I say is never, okay, but you say likely, that have some problem. Because when I say never, which means that that characteristic never appear. But if you do not notice that part, it will be served as a warning. Okay, so for each cluster, indicate how likely the Munger illusion is occurred during the cluster process. From my perspective, I was thinking about noise actually will generate an illusion. So the K-mean, yes, I think it's very possible. Why? Because K-mean actually will be affected by noise a lot. How about K-medioti? Actually, it will be less impact as compared to K-mean. So that is why you find out I reduce the degree. And this hierarchy clustering algorithm, it was not as serious as K-mean, but it somehow was still related. How about DB scan? From a perspective, I will mark them as unlikely because I feel the DB scan already eliminated the noise at the very beginning. Okay, and SNN clustering, they are also eliminated noise at the very beginning. So that is why you will find out the degree are different. Okay, so then the next one, K-mean, how likely is the same object appear to belong to different clusters due to the following reason. Okay, K-mean, remember it's K-mean. Nearby object create the illusion of similarity. Yes, it's possible, right? Because if there's noise in the data set, yes, that is possible. Random initialization make object group differently, yes, that is possible. Okay, changing the number of the cluster affect the grouping, yes, that is possible. Sensitive to parameter choice like epsilon and minus point and similarity threshold, unlikely. Or you can say never. Okay, because we don't change epsilon, we don't change the minimum point, we don't change the similarity threshold. Okay, you can do unlikely or never. Okay, I should choose it, never. Okay, fine, but I think it's these two. How about K-medioti? How likely the same object appear to be the different cluster due to the following reason? Nearby object create illusion of similarity. It will be possible. Noise in the data set, it will be very possible. And random initialization, yes, it's possible, but it's not as strong as a K-mean. Changing the number of the cluster affect the grouping, yes, that's possible. Sensitive to parameter, that should be unlikely or never. So if you write never and unlikely, I all think they are fine. How about for DB scan? Okay, DB scan, nearby object create an illusion, maybe it's possible. Noise in the data set, yes. Even though we say noise probably will be limited, but if there are too many noise, it was still possible. It probably is the most possible thing as in the DB scan part. Random initialization, make object group differently. That part I say never. Why? Because we don't do random initialization in the DB scan. Okay, and changing the number of the cluster, we say never, because we don't change any parameter. We don't have the concept, the number of cluster, how many number of cluster and how need to be specified, we don't. Okay, so that is a never. But if you do likely, somewhat like, if you do unlikely, I think it's fine. But if you do somewhat likely, you need to be care about that. Sensitive to parameter, like it's very likely because your epsilon, minimum point, or similarity threshold really affect how the result looks like. Okay, so then that is the part that we want to make you to understand there's a different clustering mechanism and how they probably will be aligned to each other. And then you will also find out, this is more like summary about our cluster. And then you will realize that we emphasize on KME-OD, and the hierarchical clustering, and the DB scan. And if there is a final exam, I think these 4 different clustering mechanisms are the most important one. Okay, so there's a final comment on class validation. This is from a book, a clustering mechanism, a book. They say the validation of the cluster structure is the most difficult and frustrating part of the cluster analysis. You need to having a strong effort, and then otherwise it will remain a black art. Okay, and you need a true believer who are experienced and great courage. That is interesting. You will see that in a computer science book. Okay, great courage and true believer. Okay, so then what kind of thing? Some student asking that, can you give me certain illustration that from last year, saying that when the cluster validation major cannot do well. So I give you the example, like this one, if the shape looks like this one, the sum of square arrow definitely cannot work well because it's not global shape. Okay, so that's the last part for our class lottery for today. For you to know that next week will be our last session before the final exam. And William is laughing because I keep reminding you about that. And then after the final exam, in the final exam, usually we were having a very quick review about what the possible question that we are going to having for a final exam. But is in this semester, we cut the association rule and from 2 weeks to 1 week. So there are many content I need to talking about the next week. And then I already upload the handout. You will find out that I have so many sections, I call them optional. Optional, which means I'm not going to teach. Okay, and why I'm not going to teach? Before I teach, but then after that I find out there's not necessary for me to teach because most of the time they were not going to be used. And also because I'm not going to teach, so those parts of the handout are very complete. Okay, if you were interested in that, you can actually check the last year's lecture. Okay, because in the end I still want to save around like 5 minutes in the end. And even though I already cut from 2 to 1, and then try to remind you about what is a possible thing we probably will having that in the final exam. But I would suggest you really need to check the exam paper. Okay, see how our style. You will find out most of our style are ask you to reason. Okay, there's some case like that. What is your choice? And reason that. Most of the time that is our question looks like. So our TA actually need to work very hard. And also, I beg you to do one thing is, I know there are so many international people right here. So when you try to write your final exam paper, don't do script, okay? Do print. You know what I'm talking about? And sometimes our international speaker usually will like, let me try to demonstrate. They will try to say something like that. And the TA is like, what is that? Okay, so please, if you do that in your paper, this one I want to say this is something. Then do print. This is an answer. Don't do this. See, TA are not going to see this one. Try to have print, write that in print. And then if you can, you know that sometimes the TA cannot recognize, they probably will give you 0. Okay. And another question is, if you write something and then you did not describe well, or like you think the TA make the wrong judgment, welcome to argue with the TA. Okay, don't argue with me. And I already get into, at the very beginning when I teach, I will be the one trying to grading the paper. And if I out with many people, and I don't want to do that anymore, so I kind of tell TA what to do, and then that, and so the remaining part go to the TA. And you can write the final exam paper in the language TA are going to recognize. So, for example, you can write in Mandarin. 你可以用中文写 okay? You can write in, how many languages we have, RTA? So then we have, you can write in English, no problem, all the TA understand English. You can write in Mongolian, Spanish, and Indonesian, and then what kind of Hindi. Okay, so you can write the language RTA can recognize. Okay, but what I suggest you write in English. If there's some special language, I would suggest you to write in English. But if you write Mandarin, it's fine because we have many TA can recognize Mandarin. Here are one of the clustering example I would like to show to you. Okay, so one example. So if you remember how the word to vec looks like, okay, and then I remember in one session I told you word to vec actually are not good for recognize the emotional word there, because you will actually say this is a good book and this is a bad book, okay, because they're having the same context word. So good and bad actually will be clustered together, will be put together. So if I actually try to show that show our embedding, okay, then you will find out bad and good actually will be put together. In one of our work, around that time we don't have the bird and something like that. We only have the word to vec around that time. We want them to become having bad and bad grouped together, and good together, and some of the concepts be grouped together. So we can not only try on the word to vec, we want to somehow cluster our embedding. So far so good? So just imagine you have so many vectors, okay, from word to vec, and then we feel like there are some cluster related to it. In one of our work, we want our thing look like this one, okay, and then we really want the cluster are somehow sentiment related, because before the word to vec are not good for it. So how can we do the cluster? Okay, so you can imagine this part, so how we try to do this one? Around that time, this is belong to one of part of the work in our lab before. We want to know that how good we are, so we can actually see right now. As I say, some of the word actually they're having their class label. Okay, so you can imagine this is some class label. But not every word have that class label. They probably will tell you Lord, God, they belong to the same category. That about religions, about the God. Okay. But then you know in the social network, a lot of people would like to have a lot of misspelling. And then something like heavens, heaven, and goodness, and gosh, and so many words. Actually, I cannot find the class label. So you can imagine that I actually was having, so except for those words in bold, they having the answer. But most of the words that are not in bold, they don't have the answer. So what we can do, we can actually cluster our information. And today, if I find out, so here we're actually talking about this one, assume that we actually cluster our data and we put Lord, heavens, heaven in one cluster. Goodness, different kind of goodness, and God and gosh into another cluster. And then, but in our answer, remember this is the answer. And in our answer set, we say Lord and God supposed should be in the same class. right? So then I consider that cluster are not good enough. So far so good? So we call them completeness. Because we have in this like 20% of the data come in, and I hope the data actually will be in the same class. But currently, based on this cluster mechanism, we don't think that's good. So we want to measure that in the same classes, how many members are actually in the end be putting into the same, in the same class. How many members are we actually in the same cluster? What is the percentage of it? So we try to call them completeness. So far so good, understand what I'm talking about? So for example, here is a 2 element, and then I will try to say, in this 2 element, how many elements actually in the same cluster? And then I actually find out 0, right? Because none of them actually in the same cluster. They do not complete. Okay, so that is one case, like this one. And then another criteria, we call them homogeneity. What does that mean? It's assume that, again, if you see the synset class, actually means the answer that we have. The 20% of the data, we have the answer, and then we know Lelore and Ga belong to one class, and badness, abuse, bad, disorder belong to another class. If you will find out in the same cluster, they having element actually supposedly should be distributed in a different class. They are not homogeneous enough. So far so good? So remember the thing we're talking about, external index, it depends on how you try to utilize external index. We try to show you the example. Here are the answers. So 20% of our data have that class. And then I can see that in the same class, okay, how many of them in the same classes, in the end they will be in the same cluster. Or actually I utilize a cluster as a unit. So in the same cluster, how homogeneous they are. Are they in the same class or actually they're being distributed in a different class? So I can calculate about the homogeneity. Okay, and then afterward, what we then do around that time, my student try to do one thing is try for many K. So here are the number of the cluster, and then he has 2 measurements trying to calculate how complete is or how homogeneity they are. And then you can actually see the different color right here. And then afterward, we actually will find out, so for example, you will realize one thing, when your number of cluster increase, okay, they will become more complete, or actually they will actually have more homogeneity, because then you actually have the less cluster. And from right here, we realize that these 2 scores actually interact right here. So that time we did not utilize L, but we utilize external index and utilize this intersection as a K that we try to working on. So for that work, we do the clustering and we utilize some sample data, and then we try the K equal to 1400 and to set up. So that our class, because the clustering is not all the work, but then here we try to demonstrate how to utilize external data to utilize different measurements to decide the K. So far so good? By the way, that is not standard textbook example. It's just an example in our lab we try to working on, how we try to utilize external index. In that external index, we define our own category. We say, we hope that the member actually in the same classes are actually can be assigned to the same cluster. Or actually we hope the cluster can only contain the member in a single class. So for each kind of cluster, we can calculate certain ways. We can also calculate that's the completeness that we're talking about. So then afterward, we actually were going to having that measurement and find out what is the K. So that is one of the example you can thinking about how we can do the external index. So far so good? Understand? Okay, so it looks like I don't have the time to go over the cluster outlier analysis, but let me try to tell you the outlier actually can become based on some statistic. Okay, so the remaining part you probably don't need to remember, but just know from the statistic point of it, we can calculate every point and the corresponding information. And from the statistic approaches, the one actually are very, very far away from the mean can be considered as an outlier. Okay, so they're having so many different kind of tests right here. But then you can actually here also having different kind of the example. But we don't want to go through them, just knowing this concept. From statistic point of it, the outlier is something very far away from it. So you can imagine from the clustering point of it, what could be the outlier? The one related to noise, right? And then that noise is really far away from all the mean. That could become the outlier. So that is the example we want to tell you about that. I'm sorry that we don't have the time to go over them because I want to spend a little bit of time about summary about the clustering. They are a key point. By the way, I think the summary of all the session about classification, about the data or about the text on NLP part, and think the clustering actually are really quite, I think they are important. So then the clustering, one thing for you to know that the intra-cluster similarity about your object in the same cluster supposedly should be high. Okay, the inter-cluster similarity between in the different cluster supposedly should be low. Okay, and we have different kind of cluster mechanism: K-mean, K-mean-OD, hierarchical clustering, and density-based cluster. And then 1, 2, 3. I think the 3 should be considered as the most important one. Okay, so let's try to compare between the difference between K-mean and K-mean-OD. K-mean, each cluster represented by the center of the cluster, and that center, this one, could be a virtual point. Okay, and the K-mean-OD and or like pattern that we're talking about, can be represented by a real object. And the limitation is if your cluster have different size, density, and their shape are not wrong, and they are not good for K-mean and K-mean-OD. How about cluster, hierarchical cluster? We spend a lot of time on trying to understand when you're choosing your distance, how you try to update your proximity matrix, actually you test mean or maximum one, actually will produce a different result. Okay, but hierarchical clustering, you don't need to determine the number of the cluster. You can actually utilize your proximity matrix to merge or split the one cluster at a time. And then if that is mean, actually will be more sensitive to the noise. Okay, and maximum, they will usually tend to break the large cluster. How about dB scan? We say the dB scanner is important, but in the dB scan, one thing for you to pay attention to is you really need to understand the difference between cold, border, and the noise point. Okay, and dB scan, since we already consider noise point, they are a little bit far away from it, or the cold point and the border point, so they will be more resistant to the noise. Okay, and when the time the dB scan cannot work well, you have different density, or like you have high dimension data. And then because of density 1, we're talking about sheer nearest neighbor approach. We try to pay attention to the common neighbor between the vertex. Okay, and then to measure the cluster validation, you have external index, like what we try to show that to you. Okay, you try certain like a 20 class table, and then we try to pay attention to if they are in the same clusters, in the same class, are they also in the same cluster? Or in the same cluster, do you consider mix of the classes from your external index? And so if that's the case, for example, the example I try to show you, we give you the completeness and homogeneity. You can also utilize entropy. Okay, see that, or if you in the same cluster, how many of them are belong to different classes. You can calculate the entropy. That is possible too. And then we can have internal index, such as sum of square error within the cluster, or actually across different cluster. You can utilize correlation by utilize the proximity matrix and incidence matrix to do the correlation. Or actually you can utilize, pay attention to cluster cohesion and cluster separation. Okay, so that is a part about the cluster validation. So that will be done for today's session.